first introduce our first speaker, Joe Moore from UC Berkeley. He's going to talk about topological band physics introduction. Thank you.
Great. Thank you very much. It's nice to be back at Rice. And today will be mostly about uncorrelated electrons. That was my charge, but I will try to convince you that not only are they interesting in themselves sometimes, but they're interesting groundwork for correlation physics. And yeah, I wish we had a blackboard so that I could answer some questions with it. I came in and I was excited. I thought those were blackboards, but they're actually just window shades. So if you ask me a question about something I would normally answer on a blackboard, I will try to use my hands, which is not a great substitute, but I would welcome questions along the way. And as kind of high-level motivation, so some of what I have to say you might have seen in courses depending on where you go to school, but I will try to tell you things that I wish I had learned when I first learned some of the stuff that's older, and then the newer stuff, most of what I have to say we didn't actually know when I was in grad school. At a high level, maybe let me give a bit of motivation for why you might care about topological materials, even at the relatively simple level I'm going to tell you about, and then Fiona Burnell will start talking about the beautiful things that happen with strong correlations. So one thing that the particle physicists have been very good at over the years is breaking up matter into smaller and smaller pieces, and aside maybe from gravity, they think they understand things pretty well. These are the particles they've found, but there are many other particles that could exist as fundamental particles in nature, but don't seem to. And the good news is that they do exist as emergent particles in condensed matter. So the Val fermion I talk about tomorrow is a famous example of something that does not seem to be there in the standard model, but is there in some solids. Another way that people in our field of emergent behavior in quantum materials get excited, sometimes we make a new particle and other times we make a new sort of fluid or a new sort of response. And that's how topological order was discovered. And that's going to be my starting point. So, but I will say a little bit about universality in condensed matter physics and what made me want to be a condensed matter physicist, and then how topology gives us a new version of that. So the sort of bread and butter condensed matter physics until about 1980, we understood almost everything in terms of notions of symmetry breaking. And symmetry is also really important for some of the newer topological states. So just briefly, the way we understood most kinds of order was in terms of the vacuum having a lot of symmetries. The vacuum you can rotate by any angle, you can translate by any angle. If we go into a crystal, for example, the set of rotations and the set of translations get broken down to some smaller discrete group, and we can classify crystals that way. Likewise, when we talk about magnets, those don't only pick out a direction in spin space, they also break time reversal symmetry. And understanding time reversal symmetry is really the key to topological insulators that are in the second half of today. Another important example, it's not limited to classical physics. When you go to superconductors and superfluids, there's a slightly more subtle notion of symmetry breaking. So this is not just philosophy, and this is the fact that when I heard it, it sort of settled me, I think, in doing condensed matter. And it's essentially just classical statistical physics. If you've ever boiled water on a stove, you've seen this liquid-gas transition, right? You go up to high pressure, you get a liquid. You go up to high temperature, you get a gas. There's a point where that transition disappears. And in fact, you can quantify its disappearance by some sort of power law. So for example, along this line, there's a density difference between the liquid and the gas that goes to zero as I approach the critical point, and that vanishes as some power law. If, on the other hand, I take a bar of iron, in principle, an Ising magnet, something where the magnetism comes from quantum spins that want to point either up or down. So totally different kind of system, very quantum mechanical, very solid state as opposed to fluid. I find that the magnetization disappears near this Curie temperature, again, as a power law, and remarkably, it's the same power law. In other words, if you sit close enough to continuous phase transitions, some things matter. The dimensionality matters, and maybe the symmetry of the order parameter matters, but all the other details don't really matter. The differences between water and a bar of iron are somehow irrelevant. And that won a Nobel Prize for Ken Wilson. That's universality at continuous phase transitions. And the discovery of the first topological phase, the integer quantum Hall effect, was an even simpler kind of universality in a way, which was people were able to make very clean two-dimensional electron gases. This was before graphene and that sort of thing. You took two slightly different semiconductors, and at the interface between them, you could confine electrons. And a standard measurement when you have a new semiconductor is to go to a high magnetic field, run a current, and measure the voltage that appears because the current is bent by the magnetic field. Normally, when you do that, it's a nice way to measure the density of carriers and whether your carriers are electrons or holes, basically. And the standard Hall effect that Hall did experiments on back around 1890 is this straight line red curve, where the red curve is the so-called Hall resistivity. Now, if you go to a two-dimensional system and large magnetic fields, you see this strange behavior of plateaus. They're very flat. They're actually quantized to about 1 part in a billion. And on one of those plateaus, I'll convert it back to a conductivity. What you get is e squared over h times an integer to about 1 part in 10 to the 9th. And this is so universal, meaning it doesn't depend on, whether your sample is very good or a little bit cruddy. It doesn't depend on whether you're doing a gallium arsenide quantum well or graphene. I mean, there are some things that care, but the fact that you see an integer times e squared over h is so precise that it's now used in defining units, actually. Of course, you don't always get integers. Sometimes you get fractions, and I leave that to later speakers. But I want to start by talking, the beginning of this field was really trying to understand essentially two different pictures of where this came from. Why do I get an integer times e squared over h? And by the way, this e squared over h is a very sort of human scale. It's of order 10 kiloohms, while E is small, H is small. Your resistance is not that many different orders of magnitude from this treated as a resistance, or I should say H over E squared is of order 10 kiloohms. So it's actually very similar quantities to what you measure in like undergrad physics lab. And in fact, I'm not going to say anything about superconductivity because my charge is weakly correlated electrons, but there's an even older measurement in solids that gives you E over H to great accuracy. So that means that just by measuring big, messy chunks of matter, you can get E to incredible accuracy, and you can get H to incredible accuracy if you can measure both E over H and E squared over H. And that's something remarkable about topological protection in quantum systems. Somehow quantum mechanics means that even a system that has some disorder and some thermal wiggling can effectively be as perfect as anything else in nature. All right, so now we come to the serious math and physics part. So the history of the integer quantum Hall effect, or I would say, well, quantum geometry of wave functions came out of the second way to try to understand the integer quantum Hall effect. And yeah, one could easily spend a whole lecture or two just on the integer quantum Hall effect. I don't have time, so I will sort of summarize the highlights, and there are books out there by now where you can read more. Basically, the second effort was by Thouless, Komoto, De Nijs, and Nightingale, and it was more or less thought of as a beautiful but kind of niche or not that useful way of looking at the integer quantum Hall effect for almost 20 years. Like if you look at citations to their paper, it was quite small, and then it blew up around 2005 with all the stuff about topological insulators. The explanation that people were instead talking about was the first one, due to Laughlin. And since this talk is more about bands and TKNN, I'm not going to say very much about the traditional Laughlin argument using Landau levels. But that's kind of what Thouless et al. Wanted to do, was explain, if you didn't want to be as unique or clever as that argument, if you wanted to understand the integer quantum Hall effect using kind of standard solid state notions, how could you do it? And in doing so, they understood for the first time that there's a kind of geometry of Bloch wave functions in the unit cell. And those turn out to be massively important all over solid state physics. And that's why I'm here today to talk about them. There's about a 40-year sequence of more and more discoveries that things we didn't really understand in solids we understand by expressing them in terms of geometrical quantities that kind of generalize what happened here. So today is going to be about insulators, not only about topology, but also about wave function geometry or quantum geometry. And then lecture 2 is going to be about metals, semi-metals, optical properties, and so on. And that's stuff done in the last 7 or 8 years, I would say, in lecture 2. So today has a bit of older stuff. I'll try to give a new take on it, I guess. And then tomorrow has more stuff happening now. So when I say that a lot of things we only understood once we had these Berry phase gauge fields, and I'm going to define what they are, but this is kind of where we're going, if you like. We've known for a long time that we can think of the wave functions in a perfect crystal of one electron as these block states that have some value of momentum, and then they also have some periodic wave function. You could think of it as the wave function inside the unit cell of the crystal. It turns out that once you realize there's a certain geometry of how wave functions depend on crystal momentum, you can understand some topological phases like the 2-dimensional quantum Hall effect and a 4-dimensional generalization. Once you add symmetry, you can realize that topological order of this kind of weakly interacting kind is much more common in nature than you would have thought. I'm not going to get all the way into all the different kinds of topological order, but people who look at 30,000 or so different crystals will often say that about 1/3 of them have some notion of topological non-triviality. I'm going to focus on the ones that are most important, like the 2D and 3D Z2 topological insulators. And then I have 1 or 2 slides on why interactions don't spoil everything and what are generalizations of this to other symmetries and so on. But I'm going to focus, because I hope we have some experimentalists in the audience, on the topological phases that are most relevant in the lab, and I only have 1 or 2 slides on how people actually observe them. I think you'll hear more from other speakers. So then, even aside from topological phases, electric polarization, it's been known to the ancients, essentially, that sometimes if you have a crystal that breaks inversion symmetry, it has a polarization. That fact was misunderstood, you could say for thousands of years, but let's say for about 50 years, even after people understood quantum mechanics and Bloch's theorem, it wasn't understood how to calculate electric polarization until about 1987 to 1990. And then there's a generalization of that I think is the last thing I might get to today, which is maybe the first example of a non-abelian Berry phase in a crystal, and that's the magnetoelectric effect. And it's okay if I don't make it through everything in blue today. If you ask me questions and I don't get through everything, that's probably good. I don't mind. And then, metals and Dirac semi-metals and so on, I'm going to save for tomorrow. Okay, so this is what I showed before. This is what we'd like to understand. And I'm going to quickly give you the kind of textbook explanation, but it will be a little bit quick. And this topological order gets used in different ways by different people. So 2 definitions that apply for states like the integer quantum Hall effect, not necessarily all topological states. Something we can measure, in this case, the Hall conductance, is given by a topological invariant. And I'll give you an example of that mathematically, but basically something that doesn't change under small perturbations. So essentially, the mathematics of topology is how do we study objects that don't change under continuous deformation? If that describes your solid, then you might expect your physical response will not change under small changes, and that's the topological robustness we want to understand. A practical definition, again, not for all topological phases, but for the ones I'm mostly talking about today, and the way that they're often seen in experiments is that even though they are bulk insulators, they have some kind of metallic edge or surface state. And how these are connected, I will say a bit about. And then a more sophisticated definition of topological order is in terms of a field theory, the kind of field theory that describes it. So symmetry breaking is described by Landau-Ginzburg type theories, basically field theories with an order parameter and some derivatives. Topological phases are described by other kinds of field theory that I'm not going to talk about, but if you like theory, you might find that interesting. To be precise, integer quantum Hall effect is described by a sort of Chern-Simons field theory. All right, so the traditional picture, if you want to connect the integer quantum Hall measurement to the simplest calculation you can do. It's to take electrons in a constant magnetic field and solve their energy levels, the so-called Landau levels. And a way to connect that to the Hall effect is the following. So just by sort of numbers or counting, you could ask, well, I told you that the Hall effect was often used to measure carrier density. So if you took the quantized value, ne squared over h, and used that to get out a two-dimensional density of carriers, you would get that the density of carriers is basically 1 per flux quantum. Flux quantum, well, okay, whether you put C or not depends on your units, but there is a h over E is a magic number, is a flux times an area, and the density of electronic states in one of these massively degenerate Landau levels corresponds to 1 electron per flux quanta. So it almost looks like when you measure the Hall quantization that your density of electrons has somehow gotten quantized. You only see densities that correspond to an integer number of filled Landau levels. So that is not a very good picture. And it's why maybe before the experiment was done, people did think there would be some kind of structure. They didn't think it would be a perfectly straight line. They thought it would wiggle and it might have approximately flat regions, but no one imagined before the experiment that there would be these perfectly flat regions. And that was that picture of that, the first successful one I'm going to give you in a second, is really a clever idea of how transport can work differently from how normal transport works. And then what Thouless et al. Did is kind of connect Laughlin transport or pumping transport to our more standard calculations of conductivity. But very briefly, these are facts about the Landau level of the quadratically dispersing electron. But a clue that none of this really matters, actually, in order to see the quantization, is that you also see the quantum Hall effect in graphene. And the structure of Landau levels, for example, their energy, looks totally different in graphene. So somehow there's something topological or special about Landau levels, and maybe about Landau levels in graphene too, that it goes beyond just the numbers. And what's really special, one way to look at it is the existence of these edge states. And I'm going to very quickly tell you this Laughlin pumping argument. I wish I could spend more time on it. And then that's really what Thouless et al. Invented topological band theory to kind of explain. So normally, when we think about conductance, we have electrons that, for example, have a certain momentum and they hit an impurity and they get scattered to another momentum. So the picture of what happens, the reason why the conductance is not perfect is your electron is moving suddenly, not adiabatically, from one state to another. The occupancy of states is changing. One was full and another was empty, and then the electron moved. And conductance like that, is often what you measure. You might measure a metallic or scattering conductance at the edges of your sample or something in the quantum Hall regime. Laughlin's point was that actually an insulator can conduct charge. To be precise, a gap system with no diagonal conductivity can have a Hall conductivity, and the Landau level is an example of such a system. So his idea of pumping was the following: take a system in a magnetic field with Landau levels, make a disk, drill a hole in the center of the disk, and put a magnetic flux through the hole. What happens if you ramp up that flux slowly? Well, a time-dependent flux gives you an electric field that goes around. It goes in the theta direction. It goes around the circle. And what Laughlin showed is that Landau level states are very special in terms of how they respond to a flux through the center of them. If I just took an ordinary trivial insulator like, let's say boron nitride or something, and did this experiment, the flux doesn't actually touch where the electrons are. It only goes through the hole. Nothing very much would happen. So a boring insulator, nothing happens if I punch a hole in it and thread a flux through. What Laughlin showed, and here's something that I encourage you to go through in your own time if you've never seen it in a course, is if I ramp the flux through the center, all my Landau level states will move. They will adiabatically move. It's kind of like the luggage carousel for those of us who spent a long time at the airport. You note that your bag stays on the same piece of metal, but the piece of metal moves. your electron stays, in a sense, in the same state, but the state moves over, and that's pumping. The states move outward, and that gives you conductance. So this is not yet anything to do with bands. It's just a very funny way that transport could happen. And if you like, the question that Dowless et al. Answered was, okay, if I don't want to think about this kind of seemingly hand-wavy picture, it's rigorous, it's not how we normally think about sit down and calculate something with block states. If I wanted to think about this, what makes some bands special? Why do some bands react to pumping a flux and others do not? And that led to Chern number, topological bands, Berry phase, et cetera. So I've used this term topological invariant, and let me give you an example that's actually very relevant. Sorry, I somehow have a little placement error. That's very relevant to what we're going to do with crystals. So topological invariants in physics often come about by global geometry. It's like you take some local geometric thing and you integrate it. And a classic example of that is if you integrate the curvature of a closed two-dimensional surface, it's effectively quantized in physics language. So for example, suppose I took the sphere. The sphere, the so-called Gaussian curvature is 1 over the product of the radii of curvature at every point. For a sphere, that's just 1 over r squared. And if I took the sphere and I integrated 1 over r squared over the surface area of the sphere, which is 4 pi r squared, I would just get 4 pi. And the magic is that that 4 pi, it doesn't care about the radius of the sphere, but it also doesn't care about whether it's a sphere or a football or an egg or whatever. However I continuously distort the sphere, the total curvature is quantized. If I took the torus has positive curvature on the outside and negative curvature on the inside. The torus has total curvature 0, but again, it's quantized. Anything like the torus will have total curvature 0. If I had 2 holes, I would have a more negative curvature than positive curvature. And that's the Gauss-Bonnet theorem. So we had a curvature, we integrated over a surface, and something magical happened. And that's what we're going to do with bands and the Chern number effectively. And the good news is you only need a little bit of band physics to start with, and that is this Bloch's theorem. And I'm going to be a little bit quick on some of the solid state physics, but again, ask me if you want me to say more. Bloch's theorem is about a perfect crystal, wave functions look like a product of a plane wave, and then a part that is periodic in R. So we can choose the momentum that appears here. It's almost normal momentum. We call it crystal momentum. It doesn't really run through all momentum space. It lives in a smaller region called the Brillouin zone, some region of K-space with periodic boundary conditions. And I think you know energy bands, band structure, blah, blah, blah. That Brillouin zone, so the set of inequivalent momenta in Bloch states, that's going to be the surface that we integrate something over. So if you're in solid state physics, I think you know the Brillouin zone. But we need to define a curvature. And that turns out not just to happen in solids, it's actually a very general property of quantum physics. And I will say a little bit about that because it's maybe the biggest thing that gets left out of undergraduate and sometimes even graduate courses on quantum physics. And I'll give you a specific example in a second, but here's the general idea. The general idea is that the adiabatic theorem, as we teach it, is only sort of half the story. The adiabatic theorem, as you've heard it, I'm sure, is if you have a non-degenerate state and you change the Hamiltonian slowly, you will remain in that state to a very good approximation. The incomplete part is that if you took the Hamiltonian around a closed loop in parameter space, that is, whatever you're using to change the Hamiltonian, and for us, we're going to use momentum, then you actually pick up a phase, and we make that phase as a loop integral around the path of a quantity that's like a vector potential. It's not obvious yet why it's like a vector potential, but I make it out of the reference wave function at every point of K-space. So some derivatives of the wave function give me something I'm going to call a Berry connection. I write it like a vector potential, and the loop integral of that might be physical. And before getting into like a little bit more about why we write it as a gauge field, here's the simplest example that again might be worth working through if you like. Because this two-level system, it turns out that the two main flavors of topology that people do, one is kind of topology of wave functions and the Berry phase. the other is topology of Hamiltonians. This is great practice for both of them. So what I'm doing here, I'm just taking a spin half. I'm applying a magnetic field of constant magnitude, Zeeman field, and changing the direction of the Zeeman field. So I could, start with the spin at the North Pole, say, or the magnetic field at the North Pole. I could take it adiabatically down here, there. And the spin follows the field adiabatically, according to the adiabatic theorem. So the surprise is that when I do this, if I take the spin around a closed path, and again, the gap never closes because the field magnitude is constant the way I wrote it. If I take it around a closed path, I wind up getting a phase. And in fact, that phase is proportional to the area enclosed by the path I went around. So it's kind of like the Aronov-Bohm phase if I had a magnetic monopole at the center of the sphere. But it just comes from carefully calculating how did my wave function evolve as I went around this path. So that's an example in Barry's paper. For us, we're going to be talking about cases where the parameter is momentum in the Brillouin zone, and A is made from block wave functions, the U sub k. But let me explain why this is like a gauge field and why everything that you might remember about electricity and magnetism, your sort of U1 gauge fields, it's called U1 because the phase change is an element of the unitary group of dimension 1. This same kind of mathematics appears all over the place now in solid state physics. So the idea of why is this like a vector potential? Well, I've got a non-degenerate state at each momentum, right? So there's no other state around, and you and I almost have to agree on the wave function of that state. The only thing we might disagree on is the phase. There's no reason why you and I would necessarily choose the same overall phase. We should get the same physics if I choose psi and you choose some different phase, and maybe that phase is even k-dependent. So psi and e to the I chi should have, times psi, should have the same physics. And there, if we calculate how does this Berry object change, it changes just like the vector potential in E and M. It picks up a gradient of the phase. Okay, that means that A itself can't be physical if it depends on this phase choice. But just like in E and M, we can make objects out of A that are gauge invariant, which means they're not sensitive to this arbitrary choice of phases. And the simplest one is what we now call the Berry curvature. It's just like the magnetic field strength in E and M. It's the curl of A. So the curl of A, both in metals and insulators, if you had to pick one geometric object to know, it's the most important one. There are a lot of others at this point, and we'll see a couple as we go along. But this is where it all started, that the curl of A, because the curl of A cancels out this gradient, the gradient disappears, this might be physical, and what physics does it control? And looking ahead a bit, if I had more than one band or more than one degenerate state, then naturally I would throw in some band indices, and this has all the structure of a non-abelian gauge field like what you'd see in quantum chromodynamics. So maybe one last comment. Working this way is not the only option. At this point, there are many different ways to represent these geometric phases. And there's one that is quite useful for practical calculations, and it probably deserves of credit because it was about almost 30 years before Berry. And it's called the Pancharatnam phase. So Berry's paper is very well written. I highly encourage you to read it. It gives a bunch of examples of what all are the same geometric phase. And Berry doesn't claim to be first. He just points out these are all the same thing, and he works a very simple example, which is like the one I just did, adiabatic spin in a field. So suppose you wanted to actually calculate the Berry phase around a loop. And a famous example, it turns out, is a loop sort of around the Brillouin zone is how you compute electric polarization these days of a crystal. Well, you could write that as, it turns out, a bunch of these overlaps. And if you slightly rearrange the overlaps, so this is now a grid, you can write it in terms of projection operators. And the projection operator is a really nice object. And what Pancharatnam realized just by thinking about 3 projection operators onto different axes in classical optics was that there's a sort of geometric phase appearing when you take products of projection operators. You don't really need an infinite number. 3 is enough. And the reason why the projection operator is really nice is that unlike psi, the projection operator is actually gauge invariant. So if you're like we just heard from a DFT person to open the session, I'm impressed that your vice president for research knows, what we do. That's nice. He would prefer something like this rather than having to invent a gauge and then have the gauge disappear at the end. If you just work with projection operators, your formulas sometimes get a little bit more complicated. There's not as much of a picture, but they're explicitly gauge invariant. So that's still useful. And then finally, where all this mathematics gets connected to physics is what happened in 82, 83, Thouless et al. And what they pointed out was, okay, if you want to understand which two-dimensional crystals or which two-dimensional bands will have the Hall effect and which will not, you can do that just by calculating the integral of the Berry curvature. And the integral of the Berry curvature, mathematically, that's a topological invariant. It gives you an integer, which the mathematicians will call Chern number, after the great geometer Chern. So in physics language, here I've written it out what F is. This says, okay, you're given a two-dimensional band, and I'll give you a famous model due to Haldane in a little while, that was important for the development of topological insulators and things like that. But basically, you take your block states, you calculate some integral, and it doesn't give you an energy or anything like that, it just gives you a number. But that number, which is an integer, positive or negative, it tells you if I were to put electrons into that band, would those electrons get pumped? Would they contribute to the integer quantum Hall effect? And they got this by, it's a fairly tedious bit of algebra, but just starting with the Kubo formula for current correlators and some massaging, they were able to realize that all the energy denominators, everything kind of non-universal drops out, and you're left with just this geometrical object. So I think in the interest of time, I'll skip this mathematical sidebar, but this is my argument that by computing the Chern number of the lower and upper state of this spin problem, you'll see that you get like negative n for the lower, positive n for the upper. They always add up to 0. You could also think about homotopy of Hamiltonians, which is what Avron et al. Did. If you really want to get into the mathematical details, that's possible, and you can ask me maybe later in the conference, but I'm not going to do it in this talk. So let me come back to, how does this make sense? Because this is saying that by calculating bulk Hall conductance using the Kubo formula, you get a non-zero number even in what we would have thought of as a band insulator, something with an energy gap. So how does a band insulator conduct charge? Well, there are two answers. One is a band insulator can pump. It can have Hall conductance even if the diagonal conductance is 0. And the other, which is relevant for some experiments, probably more experiments than the pumping one, is whenever you have a bulk band with some non-zero integer, that predicts a certain number of edge states at the boundary. So those edge states are very special. Instead of being like normal wires with current running in both directions, the reason why they have the right symmetry to contribute to sigma xy is that current only runs in one direction, and that's the integer quantum Hall effect. So if you like, the topological invariant of the bulk states tells you what has to be going on at the boundary, and that's called a bulk edge correspondence, if you ever hear that phrase. And this idea is what wound up, well, this idea and a more subtle version of TKNN is what was kind of discovered 20 years-ish after TKNN and led to topological insulators. So you'll hear two different pictures of why the bulk topological invariant gives you an edge state. There's kind of a sloppy picture, which is if everything evolved very smoothly, you would say that I've got some topological non-trivial number here, some topological triviality of the wave functions here. The only way to change, if it's really a topological invariant, the only way to change from, say, knotted or non-trivial to trivial is to violate the assumptions that let me define the invariant. The assumption was just that I had a gap, so it must be that the gap closes in between. And for a smooth edge, this is a fine argument, but actually the edge state is there even for a sharp edge in this case, not in all cases. That's one reason why this one is especially important. And that's this pumping idea, that if you're pumping a flux through the middle, you're kind of depositing charge adiabatically at the boundary. And there has to be somewhere for that charge to go. It can't just disappear into the vacuum. So Halperin is the one who really clarified that there has to be an edge state in order for Laughlin pumping to put the charge somewhere. And that by edge state, I mean something gapless where the charge could sit as it gets deposited adiabatically by pumping. All right, so now we leap ahead a bit, because band geometry, I think it's fair to say, aside from things like electric polarization, for topological phases, there was kind of a quiet period from integer quantum Hall effect to topological insulators. A lot of stuff was happening on the strongly interacting or fractional side, though. So some kind of topological invariant, again based on the Berry phase, even without a magnetic field, even without time reversal symmetry breaking, is going to lead to some kind of edge or surface state. But there are a lot of differences, even though band topology is still relevant. I would say the key differences are, instead of magnetic field, these are usually driven by spin-orbit coupling. Instead of being limited to 2D, this happens in both 2D and 3D. And the way it was experimentally detected is very different. But the good news is this topological insulator kind of band topology appears in a lot of big chunks of 3D material around room temperature. It's no longer such a hard thing to look for. So this, when I say unusual, the Dowless picture of the quantum Hall effect people perceived it as a very nice idea, but then they kind of put it away because you don't really need it for Landau levels. And Landau levels are a good description of most two-dimensional electron gases. But when it comes to crystals or nowadays moiré materials and so on, then we do need to think about the Brillouin zone, and then we do need all these band topology ideas. So the origin, and this started as an idea even before the mathematics was totally understood, is to think about things like spin-orbit coupling, which is there in essentially every crystal. So spin-orbit coupling is a relativistic effect. It's there in almost every atom. And the simplest kind just couples the orbital angular momentum, so how an electron moves through space, to its spin angular momentum. And this is different from a magnetic field. This doesn't break time reversal, which is why it's there in basically every atom and so on. But if you fix the spin, let's say if we fixed its spin up, then this would be like a momentum-dependent force. So if you wanted a rough caricature of what spin-orbit coupling is, it's like a magnetic field that's one way for spin up and the other way for spin down. And people realized that, and they had the idea of making cooked up, somewhat contrived versions of spin-orbit coupling where you would get an edge state with spin up going one way, basically spin up in an integer quantum Hall state with the edge mode going one way, and spin down in an integer quantum Hall state with the electron going the other way. And this, until 2005, people, I think, were fairly skeptical. Because of the following reasons. It was thought that this wouldn't be stable once you put in more realistic spin-orbit coupling. And the reason for that is in real solids, you can't really pick a magic direction z so that the up electrons and the down electrons separate and don't talk to each other. We thought that the moment you add a little bit of disorder, these will mix with each other, it will localize. We knew that one-dimensional quantum wires are very susceptible to disorder, they tend to localize. So we thought that we would lose the edge state. And even if this, even if you could make it, it would be two copies of the integer quantum Hall effect that don't talk to each other, and we kind of understand the integer quantum Hall effect. So what really happens is it's not just two copies of the quantum Hall effect once you make it more realistic, but there is something that's stable. But what's stable is not an integer. And I'm not going to get into the mathematics of the topological invariant until we come to 3D, where it's a tiny bit simpler, but still pretty complicated. But the physics of why there's a Z2 invariant, that I think I can explain just by thinking about the edge. So what Kane and Melis showed in a pair of papers in 2005 is that there is a stable state, which we now call the two-dimensional topological insulator, if I have strong spin-orbit coupling in some two-dimensional materials. And it does have an edge that looks a bit like this. There is a topological invariant that protects the edge, but it's not an integer. It's only odd or even. It's what we call a Z2 invariant. And I want to give you a sketch at the boundary of, where does this odd even effect come from? So let me, so I think before coming to my analysis of the edge, now is probably a good time to actually write down a lattice model that you could calculate Chern numbers and even get a topological insulator out. And it was important. It's the model that Kane and Mealy used to show that this is possible. So Haldane wrote down a model to kind of make a point, if you like, which was that you don't need an overall magnetic field to get the quantum Hall effect. So he wanted to make something like a quantum Hall state, but with zero average field, arguably. So he made a model of something like graphene. This was before the experimental discovery of graphene, but it was the same, honeycomb lattice. And he sort of made a model with electrons that would be in an integer quantum Hall state. And then what Kane and Mealy did was make two copies of the Haldane model, one for spin up and one for spin down, and verify that you could stabilize the edge, but only if you had an odd number in the integer quantum Hall effect of each spin. So that's where we're going. And here's the model itself. So there are going to be a couple of terms, but here is, I'll call it the Kane-Mealy-Haldane model. So Haldane wrote out the version where you don't think about spin, and then Kane and Mealy added spin and discovered the Z2 invariant. So the model is going to be graphene. That's the first term, which is spin-independent nearest neighbor hopping on the honeycomb lattice. And you've probably heard at this point that this has an unusual band structure. Instead of having a Fermi surface, it's a perfect semi-metal with Dirac cones and Fermi points. If you wanted to make a boring insulator, well, okay, boring maybe sounds judgmental. If you wanted to make a non-topological insulator, one way you could do that is without having any spin dependence. If you go from graphene to boron nitride has the same lattice except that half of the atoms are boron and half of the atoms are nitrogen. And we could model that as just a staggered potential where this psi is +1 on one sublattice, -1 on the other sublattice. So if you do this, this is an example of how the graphene cones are somewhat stable, but not perfectly stable. If you add this sublattice staggering, you open up a gap, doesn't depend on spin, it's just an ordinary band insulator. And that's a simple picture of boron nitride. Now let's add some more interesting terms. The first one is basically the kind of term that Haldane thought about, except I threw in an extra SZ. So if I just fix spin to be up, what this term represents is second neighbor hopping. So instead of hopping nearest neighbor like in graphene, I go two neighbors. And there is a complex phase. You can see there's an I in front. So this term, if I fix the spin up, it would break time reversal. It turns out that having the product ISZ is enough to bring back time reversal symmetry. This is the term that Haldane cooked up and showed is enough to give me, instead of the semi-metal or the ordinary insulator with all Chern numbers 0, this can give me Chern number, say, +1 for the upper band, -1 for the lower band for one spin, and the Chern numbers are flipped for the other spin. So this was the spirit. Kane and Mealy are the one who thought about spin. And this is the spirit of the original quantum spin Hall models. You have upspin, you have downspin. They don't talk to each other. It's two copies of the Haldane model. And then the bold step they took was, let's make this more realistic. Because here, if I just have this term, SZ is conserved, that's not the way real solids tend to work. There's always a little bit of other spin directions. Maybe this other directions would destabilize it and so on. So they added a so-called Rashba spin orbit term, which exists when your graphene is sitting on a substrate. The important thing for us is that this breaks the SZ conservation. And before they wrote their paper, many people would have thought that this term, if it's there, will destroy the integer quantum Hall effect and take you to an ordinary insulator or to a metal. It turns out that this partly does, but partly doesn't. It brings all your odd numbers the same, and it makes all your even numbers the same, but odd is still different from even. And that, I think this is probably more detail than I need. That's what I want to give a picture for. So basically, if I had a special direction of spin and I could break my bands into up and down and they didn't talk to each other, then I could define a spin Chern number for each band and I would get sort of copies of the quantum Hall effect. But that's not really the way solids work. Instead, every band pair, including up and down, has a Z2 invariant. It's either even or odd. And I want to give what I think is the simplest picture of why that even and odd exist. And there are various ways to write the topological invariant for either even or odd, but that gets a bit technical. So again, one of those things you can ask me at coffee if you're curious. It's nicer in 3D. But just like Chern number, the state of the system is given by the overall Z2 sum of all the occupied bands. So here's the picture of, why is there an odd-even effect? And it all comes down to something you might have learned in introductory quantum mechanics, but probably forgot unless you're an atomic or nuclear physicist. We don't always think about it that much in solids. So there's a deep fact from the early days of quantum mechanics, and this is one of the neat differences between half-integer spin and integer spin. So let me remind you of all the one electron problems you solved in like atoms or whatever. Time reversal invariance means that if you have a state, you can time reverse it, you can make a different version of it with time going in the opposite direction. And if your Hamiltonian is time reversal invariant, whoops, sorry, getting a bunch of announcements about the eQMA spring school that kicked me out of Zoom. Ooh. All right, I think I'll get back in a second. It's having to reconnect to Edgeroom. Well, I do have my slides uploaded in case that helps. Could switch to those. Yeah, do you have a way to switch to the... I uploaded my slides to the site, so I think they're on this computer. Do you have a way to get that going? Do you understand what so my slides are uploaded to the conference website. Is there a way we could show those? I think.
Which website?
Well, I guess he's getting the technical person. Don't know why my internet suddenly went down. It seems to be, but all right, now maybe it's working. Maybe not though. Okay, well, it may have come back. Let's give it a try. All right, I seem to be back. Sorry. Okay. All right. All right, well, we got a little break. So now here's the fact that you learned is basically that every state is degenerate with its time reversal conjugate. If you have bosons, if you have integer spin particles, that could be the same state, like a spin zero state is often its own time reversal conjugate. The special thing about half integer spin, which is related to the fact that the square of the time reversal operator is like rotating by 2 pi, according to Kramers, and rotating by 2 pi doesn't give you +1 for half integer spin, it gives you -1. That forces what are called Kramer's degeneracies, which is the following statement. Every state of a half integer spin in a time reversal invariant Hamiltonian is degenerate with its time reversal conjugate, but different from its time reversal conjugate. It can't be the same state. In a simple picture, that would be saying that I had an up state and I time reversal conjugated it and I got the minus state. So if I now think about my edge, this is a picture of energy and momentum running along the edge, then this scattering process, which would normally be what destabilizes the edge in the presence of disorder, that's actually forbidden because it would mix and split the two states of a Kramers pair. So this right moving mode, the only state it can be paired with is that left moving mode, and you can't scatter with the time reversal invariant perturbation within a Kramers pair. So somehow, and this was really the insight, I think, of Kane and Millie, that in hindsight, normally we would say this is a one-dimensional wire, so if I add disorder, it will backscatter and localize and not be a conductor anymore the moment I have any disorder. But if I have half of a quantum wire in the sense of one right mover and one left mover, that's actually stable. However, if I have a normal quantum wire, then I can scatter from a right mover to the left mover that is not its Kramers conjugate. So it turns out that the normal quantum wire is still unstable. Anderson was right. But the half of a quantum wire could be topologically protected. And indeed, that's what's protected by the bulk Z2 invariant. And what people really measured was that edge state, that you can have a big insulating two-dimensional chunk of material that conducts more or less like one quantum wire because it's got half a quantum wire at one edge and half a quantum wire at the other edge. And that was the 2D topological insulator. And then not very much later, people realized, again, this is what's special about mercury telluride quantum wells. I think Peter Armitage may be saying a little bit about experiments, so I'm going to skip over that. A surprise is that unlike the integer quantum Hall effect, so if you study three-dimensional band structure, you never hear very much about the Chern numbers of your bands. That's because there isn't really a three-dimensional version. You could ask about sort of, there are really three Chern integers, but they're all for the two-dimensional planes in the Brillouin zone. So there's no truly three-dimensional integer quantum Hall effect. Again, you'll have to trust me on that. There is a truly three-dimensional Z2 topological insulator, and it has a surface state, and there's kind of the original or old-fashioned way to get that, which I won't go through. I'll focus on the experimental consequence, which was pointed out by Foucault and Milly, and then maybe, as time permits, say a little bit about a deeper or more modern way to look at the three-dimensional topology. Just like in the two-dimensional case, we would expect to get a surface state that is something like half or less of a normal metal. What I mean by that is, in the 2D topological insulator, we had a surface state that was half of a quantum wire. It only had one right mover and one left mover. What happens now is normally, whenever you have a normal two-dimensional metal, you should think of, once you include spin, there are always two sheets of the Fermi surface, like one spin up and one spin down. Or even with spin orbit, if you draw a constant energy cut, cutting the Rashba band structure, for example, you always get two sheets. What's special about the two-dimensional metallic surface of a three-dimensional strong topological insulator is that it's only got one sheet of the Fermi surface. And that was basically measured with photoemission. So roughly, you take what Einstein actually won the Nobel Prize for, which is the photoelectric effect, and you spend 100 years and $1 billion doing it better and better, and it becomes a really good technique, especially if you want to measure band structure of surface states, or, well, band structure of anything, but you can tell surface states are distinct from regular states. You send in a photon, you bounce out an electron, and doing that, David Shea et al. And Zahid Hassan's group were able to see a surprise in, well, originally bismuth telluride, but this data is from bismuth selenide. So the surprise is the following. This is a material that had been studied for many years. It was even used in thermoelectric refrigerators and things like that. And it was known to have a bulk band gap from about 0 to minus 0.3 eV on this plot. And that's a small band gap by normal solid state standards, but it corresponds to a pretty large temperature because an electron volt is 12,000 Kelvin. So 0.3, this is well above room temperature. It's thousands of Kelvin. And in that window where there are no bulk states, there is actually a surface state, and it looks a bit like a Dirac cone. So that was the experimental discovery of the 3D topological insulator, the first topological state in 3 dimensions. And the reason why I went a little bit quickly over the theory, there are different ways to do the theory of it, but the way that I like now, and there were other experiments like STM as well, and maybe Peter will pick other experiments to talk about. I guess what I might do is make a few closing comments and then leave a couple minutes for questions and come back to more on the 3D theory in a second. Let me touch on some big developments in condensed matter theory that were also triggered by quantum Hall effect, TKNN, et cetera, and relate to stability to disorder and interactions. So when I turn on disorder and interactions, a couple things could happen. One might be that all of my topology goes away and things just get localized. Some things are not very stable to interactions or disorder, but most things are stable to disorder. And at the level of one fermion, people actually understand quite a lot. So this famous 10-fold way table it turns out that once you think about one particle, one fermion problems in disordered systems, there are, in a sense, 10 different symmetry classes they could have. So this is forgetting about all crystalline symmetries because it's disordered. So for example, the integer quantum Hall symmetry class, which is no symmetries, I've broken time reversal and all that, that's class A, and you can see there's an integer quantum Hall effect, an integer, this is Z in 2D, same in 4D, same in 6D, same in 8D, and so on. It turns out that everything is periodic in dimension with dimension 8. Again, this is a beautiful piece of mathematical physics that most of it is only of limited relevance to experiment because a lot of the excitement is in high dimensions and all that. But maybe the deep fact is this lets you take things like the topological insulator. So for example, the topological insulator where you have time reversal symmetry, but nothing else, that's A2. And then you've got Z2s in 2D and 3D. The other classes, they often have to do with quasi-particles and superconductors. So the way you get 10 classes, there are two symmetries that matter. One is time reversal, one is a kind of particle hole or chiral symmetry in superconductors. But at least stability to disorder, we kind of understand, and it's this beautiful 10-fold wave table. Stability to interactions is much harder in general. So sometimes interactions just give you totally new states that you couldn't understand at the one fermion level. And the fractional quantum Hall effect is the first experimental example of that. But let's ask a different question, which is, suppose I did all the work to find some quantized state at the one electron level. Is that state still going to make sense once I add interactions? And what does make sense mean? So that depends a lot on the system we'll talk about. It depends on the topological invariant, and it also generally depends on whether we're talking about metals or insulators. In general, insulators are nice. When you have an energy gap, most things are at least a little bit stable because it's hard to, a small change is not going to mix things across the gap. There's a better argument that you can make for the stability of the integer quantum Hall effect, which is that actually, with very little work, you can redefine the Chern number so that it works in an interacting disordered system rather than just a band structure. So Chern number is much better than most topological invariants in some ways. Like, you can't really do this as well for the Z2 topological invariant. The Z2 topological invariant is not as well defined with interactions as the Chern number. And the trick to define the Chern number in an interacting and possibly disordered system using the many-body wave function is this twist trick by New, Thales, and Wu, just a couple of years after TKNN. And somehow, this sort of topological invariant of many-body wave functions, that's an area where I think there might still be some interesting work to do. I don't think we fully understand when we can do this and when we can't, and other ways of doing it and so on. But here's the idea. Before, I was thinking about the Brillouin zone, and K was the crystal momentum. Let me think about what sounds like a funny system. I want to take my original system and have it live with periodic boundary conditions, or you could think about it as living on a torus. So real space torus. And with that real space torus, instead of crystal momenta, I'm going to introduce an object that would reduce if I had non-interacting electrons and a perfect crystal to crystal momentum. It turns out that you can sort of view crystal momentum as boundary conditions that are not exactly periodic. When I move, say, from the top to the bottom, or it's like moving around one of the circles of a torus, I pick up a phase. It's like an Aronov-Bohm phase from having fluxes through the circles of the torus. So that's a bit, harder to picture than just the Brillouin zone we're used to. But you can really think of the Brillouin zone as something like a torus, and Kx and Ky are fluxes through different pieces of the torus. And the good news is, whatever my many-body wave function phi naught is, I can stick it on this geometry, and I can ask, how does the many-body wave function respond when I change the fluxes? And that gives me the many-body Chern number. And again, the many-body Chern number does tell me how much does that many-body state, if I were to pump, contribute to the Hall effect. So that's the story of how some invariants are at least stable interactions, but nothing here would capture the fractional quantum Hall effect. For that, you need really new ideas that I think you'll hear about soon. So I think with that, I'm going to wrap up for today, and I'll cover some of this next time, but let me show you how far we got. So we're talking about physical states and properties from Berry gauge fields, which is maybe the most popular approach to band topology. We got through the quantum Hall effect and topological insulators. I want to say a little bit about electric polarization and the magnetoelectric effect and the non-abelian Berry phase in 3D. And then we'll go back to things that are very simple. Actually, arguably, metals are even simpler than all the integer quantum Hall effect stuff. And we now believe that a lot of what we see in metals is Berry phase effects, and the latest stuff I'll talk about is quantized things in nonlinear optics. So with that, I think I'm at my hour. Thank you very much for listening, and I would love to have a question or two.
Hi, thanks for your nice talk. I have two questions first. You mentioned there is a magnetic Boolean zone, but in actually in real material, the magnetic structure can have some incommensurate order. Then that means your Boolean zone boundary will go to infinite in real space and pretty tiny in the residual space. So how to deal with such kind of problem?
Yeah, so what we often do, and this appears in moire materials as well, so there are many systems we care about that don't truly have a real space unit cell. So what we often do is make an approximate model that does have a unit cell, and at least for insulators, we expect there to be some kind of protection or continuity. So in other words, suppose you had, in reality, and no unit cell, you had a truly incommensurate magnetic structure. Then you might model that by saying, okay, let me take 1,000 of the crystal unit cells, and then maybe the spin wave or whatever has not come exactly around, but it's close. So I'll make a model that has a unit cell, compute my integers in that, and then I will get out something that I think will still describe the truly incommensurate system. So that's one approach. That would be the old-fashioned approach, which is kind of like what Dowless did. I mean, as a simple example, if you wanted to make Landau levels in the Hofstadter model, you sort of make a continuity assumption. It is possible to define Chern number, at least, even in a system that really has no unit cell without thinking and there's this Chern marker. I mean, there's a way of doing it. I don't think it gets used that much for magnetic materials, but it gets used for strongly disordered materials. One of the people who's worked on that a lot is Terry Loring, L-O-R-I-N-G. That's been his baby for a while. So there is a way. Why it works is a little hard to explain. It's quite mathematically sophisticated, but there is at least a way to define Chern number even in a truly disordered system with no unit cell. It just would take us a little bit outside of the Berry phase gauge field.
Thanks. I have another question. When you introduced this topic, you mentioned because why do we need a topology? Because there is an electron that move around during the adiabatic process and go back to the normal the beginning point, and you find out you have some extra phase that is come from the AB phase, and that can be explained by a virtual magnetic moment. This is the reason why we need the topology. But you can find out in this process, your electron is moving within an orbit that is a 1D line, and but the Chern number is the integration over the 2D phase. So there is any connection?
Yeah. So the example of moving around a line is not really a Chern number example unless I wanted to try to enclose the whole sphere. So okay. I'll give you an example of how you can get something topological out of this. But if it's just a small curve, you might say, well, it encloses the area, but the area is not quantized, and that's true. But if you want something topological, a sign that there's something topological in this problem is, well, I could take the area inside, or I could take the area outside. I go around one area in one way, but it's on a sphere, so there's no. I ought to get the same answer whether I think about the inside area or the outside area. And the difference between those is basically the integral of the Berry curvature over the whole sphere. And And the fact that the integral of the Berry curvature over the whole sphere gives me an integer is actually why I will get the same phase computing with the area inside the loop versus, well, the area, outside the loop is actually the area inside the loop. It's just taking a different direction of going around the loop. So there is, even though you could say, well, this just gives me an area and that's not topological. The fact that the area here gives me the same phase, e to the I gamma, as what I would get if I took the sphere minus this triangle. That only works because of the Chern number, actually.
Thank you.
Sure.
Let's thank the speaker again.